get this device working. Yeah. This microphone may not work for the room, but it works for the recording. So it's my pleasure today to introduce Professor Khurram Afridi from the University of Colorado Boulder. It's a pretty well-known place of power electronics, as you know. The title of his talk is Ultra-Efficient, Compact, and Long-Life Power Electronics. Khurram is presently an assistant professor of electrical, computer, and energy engineering at the University of Colorado Boulder. He received a BS degree in electrical engineering from Caltech, back when there were a few fairly famous folks teaching in that place in power electronics, Shook, Middlebrook, and those kind of folks. And then he came to his senses and went to MIT to get his S7 and PhD degrees. And then after that, he actually he spent 10 years as an entrepreneur. First, he was the CTO and COO of Technologic, which came out of his PhD research. And then he also was the founding project director of the Luz School of Science and Engineering in Pakistan before he returned to an academic life. I got to know Khurram quite well. He was a visiting professor for a number of years at MIT in my laboratory. But over the last few years, he's now spent time at CU Boulder. He's received a number of awards, too many to read, but you may be interested in knowing that he also received, as well as we did, one of the Google Little Box Challenge Academic Awards, so there's direct competition going on. All right, so let's welcome Khurram.
Thank you, Robert. Thank you, everyone, for attending this talk and for Robert and Phil for inviting me. I'll talk about a number of topics today, but let me start by sort of telling you why power electronics is so exciting. Of course, your being here is testament to that. But let's begin with a more sort of formal introduction. So one of the things that excites me about power electronics is the role that it can play in transforming how we use energy. Clearly, we spend too much, and it's not sustainable if we're going to leave this a greener, brighter place for generations behind us. And sort of one way to kind of look at that is through this pie chart, which shows you how much of the electrical energy that we consume comes from renewable sources versus sources that are depleting, right? And while we hear so much about wind and solar, the reality is that actually all of that gets buried away in this little other, right? It's like 3.7%. Now, these numbers may have changed slightly since when I took this pie chart down, but they're not too far off. Any renewable sources that are of sort of substantial numbers really are hydro, and then nuclear really isn't renewable, but at least it's not doesn't have carbon emissions associated with it. Much of what we use, 2/3 of it, is really from natural gas, oil, and coal, and sort of other fossil fuel type products. What's the downside of this? Well, depends on your perspective. If you care about the environment, it potentially can avoid disasters such as these that we saw out in the Gulf of Mexico. Or if you're paying the bills yourself, you will be if you are not already. It sort of hits you in the pocketbook. And I like this slide here where fuel prices, which may have kind of come down a little in the last few months, were sort of skyrocketing, and it's really the first one that you may eventually have to give figuratively in order to drive a vehicle. So really, what can we do? We talk about all of these new technologies, LED lighting, and I'm sure we have LED lighting in this room, provides a opportunity for real improvement in the way we kind of consume energy. Renewable sources, again, I'm told there's going to be lots of solar panels up on the roof of this building. There's certainly a lot of wind power and solar that's going up in various parts of the world. Both of these require what? They require power electronics. If you're going to deploy large amounts of them in the grid or as standalone usage, depending on where you're going to put them. Not only just as interfaces for these, which is sort of what interests me, which is sort of the edge of the grid power electronics, but also for those of you or other people who are interested in the power system as a whole. There's lots of power electronics to play a role in sort of the interfaces between the various stages of the grid, between different voltage levels for various sorts of applications. So that's really the opportunity we're looking at. That's why this field is so exciting, and that's why I presume some of you are here. In terms of sort of another related set of statistics, currently there is about 30% of the energy that flows from generation to usage that actually passes through power electronics. Right? Again, this number is slightly dated, so may have changed a little bit, but that's sort of the best reported number in literature. And these new things that we have talked about, renewable sources on the generation side, sort of more efficient ways of using energy, whether it's LED lighting or electric vehicles, and then everything that goes in between, whether it's energy storage, high voltage DC, solid state transformers, those kind of things. These are all the sorts of applications that are emerging that interest us power electronics people. And again, these statistics have to be taken with a grain of salt because you could actually outperform some of these based on some estimates. But as a very conservative estimate, I'd say that if you were to sort of change this number from 30% to 80%, which is what people are projecting, then you can reduce the amount of energy that we consume in electrical form by at least 15 to 30%, and possibly even more. So that's really the motivating factor for all of our work. What do we need in order to achieve such a vision? Well, we need more usage of power electronics, and we need power electronics that is better. Better in terms of efficiency, better in terms of smaller size, so it can sort of fit into places where otherwise it would not if it was too big, more reliable, and less expensive. There are obviously other parameters of interest, but these, I would say, are the four foremost things that concern us all, and certainly concern me and all of you, I think, in this room. I work in areas related to all of them. Today, what I'm going to do is focus on the first three, because it's a little harder for us academics to really talk about costs very scientifically. There are ways to reduce costs, and I think that's an exciting area where a lot of work still needs to be done. Some of the work that I've done in reducing costs is really at the system level, where you can take different converters and you can build systems more optimally to reduce the overall system cost. But I'll leave that for a different talk. Today I'll talk mostly about the first three things, which is making converters efficient, making them smaller, and making them more reliable. All right, so a little bit about my research group at Colorado. We are a group of, well, you see 7 people here. One of them has graduated, so we're really now, we're a graduate student group of 6 people. All of them are working in the areas that I kind of described, building sort of converters at really low power, so 10 watt or so, going up to higher power, a few hundred watts or so. And then one of our more recent projects is at 6.6 kilowatt, which is really the largest thing that I'm building right now. So that kind of gives you a range of, in terms of power levels. In terms of applications, here are some of the applications that we're currently working on. These range from power supplies, whether they're for DC distribution systems, or for telecom, or point of load kind of applications, to solar photovoltaic inverters. This includes our Google project, as well as LED drivers, both offline as well as automotive applications, electric vehicle chargers, and these sort of at an exploratory level. We're also looking at some wireless techniques to do charging for electric vehicles. Again, I'm going to sort of cherry pick a couple of topics for today's talk. But if you have questions on any of these things or anything else I may have sort of mentioned in passing, you're welcome to ask me either during this talk or afterwards. So here's the outline for today. Essentially, I'm going to talk about a project where we've been working on ultra-efficient compact power converters that achieve high efficiency across wide operating ranges. And then I'm going to talk about some work that we've been doing actually for a while on long life AC-DC converters. Right? And then I'll summarize. Okay, so let me dive right in into ultra efficient compact power converters. And here, really the motivation for this work came from the realization and also some standardization that is happening in the both in the industry as sort of consortia as well as from some government incentives to try and build converters that are efficient not only at one or a small region of their operating range, but rather across a wider operating range. So it's just like, for example, in solar microinverters, there was the CEC efficiency sort of number, which really came about by calculating a weighted average efficiency. There are similar things that have emerged either from the 80 plus standard or the Energy Star standard, which sort of give you incentives to get a sort of a bronze rating or a silver rating or a gold rating or a platinum rating based on how well you do in terms of efficiency, not just at say 50% of output power or 100% of output power, really in a weighted sense. Now your typical converters don't achieve that sort of efficiency. A second thing that I've kind of been talking about is that at the same time that you're trying to achieve high efficiency, you're also trying to make these smaller. And one approach to making converters smaller is to really focus on, and it's the predominant way you focus on them is by focusing on their energy storage outputs. So you try and reduce the size of the inductors and the capacitors in your converter, which typically dominate the size. And you do that by increasing the switching frequency because that requires less energy to be stored in the energy conversion process. Now, as you increase switching frequency, as all of you know, you have the problem of switching losses which go up with switching frequency. So then you start looking for soft switching techniques in order to reduce those losses. And as one approach in terms of reducing the switching losses is to move towards designs which are resonant in nature, or resonant converter architectures. So especially when you're going up for very high frequencies, resonant converters are an attractive approach towards making them. The LLC resonant converter is one particular topology of the resonant converter which has been very well studied recently and is touted for having a fairly good efficiency across wide operating ranges. Here I show you one such converter, and even here you can see that as the output power of this converter is reduced down to say a tenth of its peak power, your efficiency is down into the low 80%. I have a hard time seeing this chart from exactly, but that's roughly correct, right? And the question is, well, can we do better than the kind of typical resonant converter efficiencies that you can get out of these kind of things? And so let's start by then exploring a little bit about resonant converters and how they are designed and controlled. Here I show by example a very simple resonant converter, a series resonant converter. And there are two standard ways of controlling the output power of this converter. So as you're trying to regulate the output voltage, because your load is changing or your input voltage is changing or something, one way to control that is by changing the switching frequency. That's the standard approach. Now, typically what you do in such a converter is that you operate this converter at a switching frequency that's slightly higher than the resonant frequency of the tank, so that you get a zero voltage switching on your switches, which means that the switch turns on after the voltage has been brought down to zero across it. And that's very useful for high frequency operation where that becomes a substantial, that half CV squared loss becomes a substantial component, especially true when that voltage across the capacitor or across the switch is high. Well, the problem is that if you're going to regulate by frequency control, you're going to increase the frequency further to move away from the resonance point. And that basically means you're going to have even higher switching losses and higher circulating losses, because now you're basically looking into a more inductive looking tank. And so you have what are called circulating currents. Essentially, your power factor you could think of is going down. Right? Also now, because you're going to be operating across a varying frequency range, the EMI filter design becomes a little more challenging because it's not really operating at a fixed frequency. To overcome that, the other approach is to use a phase shift control where you run this thing at fixed frequency, but you basically change the phase shift between the two inverter legs, and therefore essentially provide a lower amount of volt seconds across this tank, and you deliver a lower current to the output, right? Now here the challenge is slightly different. Here these two figures, if you kind of look at them carefully, the first figure, which is on this left, shows you when you were delivering full power. Now here you have basically each leg or both of these inverters switching at 180 degrees out of phase, which we call in phase, just because that's easy to kind of remember, but they're essentially exactly 180 degrees out of phase. And this is really a cartoon, but what you can see is that the current, which is going to be sinusoidal because of the presence of the resonant tank, is crossing through zero close to when these transitions are taking place. In actuality, in order to run this with ZVS, you will slightly run this at a frequency slightly above the resonant frequency, so you achieve a slightly negative current at turn off, so you can soft switch these devices and achieve zero voltage switching. But that I'm going to ignore for this cartoon purpose. But you can essentially assume that that's what's going on here when these going through zero here. And then on the other side, again, it's going through zero when the second transition is taking place. Right? And that's true for both of these inverter legs. So all of these switches are able to soft switch in that condition. Now, as you phase shift these, you're going to phase advance one leg, this one in this case, the leading leg, this is phase advanced, and that one is phase lagged. And so the new output voltage waveform has lower volt seconds and basically produces a lower current. But now the currents through the individual inverter legs or through these individual switches is no longer passing through zero close to where the transitions are taking place. In the case of one leg, with the lagging leg, the current is now essentially is going to zero before that transition takes place. So this leg essentially looks into a capacitive load, and then the leading leg essentially looks like an inductive load or a highly inductive load. So in the inductive load, you just have sort of more circulating current, but you still get ZVS. Here in the lagging leg, you actually are going to lose ZVS switching. Right? So that's really the problem with this kind of an approach. So the question is, can we fix this? Is there a topology or an architecture where we can resolve this problem? And that's what I'm going to talk about first. And the way to kind of think about it is that the standard resonant converter is essentially an inverter feeding some transformation network, which is LNC network with possibly another transformation or a transformer inside as well, and then a rectifier. That's how most resonant converters are architecturally designed. What if we, instead of having one inverter feed a resonant tank, we have multiple inverters feed a single resonant tank and potentially have multiple rectifiers on the other side? Okay. Now, we don't have to do both at the same time. We could. The first approach, and actually the only approach that I'm going to talk about here, is where we have multiple inverters feeding into a resonant tank with a single rectifier. We've also done work on the opposite approach as well as the combined approach. All right, so let's look at this, how we could implement that. So one implementation of that, which is suitable for a low to high voltage conversion, is shown right here, where we have a transformer that provides us a gain. And we have essentially the same series resonant tank, except it's shown on the secondary side here. We have a rectifier, which is just a half bridge diode rectifier. You use half bridge because you want to get an extra gain step from here. And then you have, in this case, we have half bridge inverters, although you could also potentially use full bridge inverters to get a gain advantage, but it's not important for the purpose of understanding how this works. All right, So what are we going to do? If I go back, I alluded to the fact that the lagging leg is starting to look more capacitive, or starting to look, the lagging inverter is looking into a capacitive load, and the leading leg is looking into an inductive load. So what if we added compensating inductance in the capacitive leg and compensating added compensating inductance in the leg that was looking capacitive and capacitance in the one that was looking inductive to essentially cancel out that. Okay, and then you could conceive that if I have some appropriate phase shift between them, because the actual amount of capacitance and inductance that I see really depends on how much phase shift I have between those two, right? Then the amount of added capacitance or inductance that I've done would exactly cancel the difference that was created. Okay, so that's the idea. Of course, when we do that, we will lose our ability to control the output by doing phase shift, because the phase shift is now going to be pegged based on this criteria. And so we could, in order to control the output power, we could resolve to some other means. We're going to keep the frequency fixed, so burst mode is the one that we're going to use to control and regulate output voltage in this case. Okay, so this converter is basically going to run at fixed frequency, at fixed 50% duty cycle, and all we're going to do is adjust that phase shift between those two legs to do the compensation, and then burst in order to regulate output power. So let's do some math to see how this works out. Well, you can compute under fundamental frequency approximation what the actual impedance is that you see into looking into these tanks at varying phase shifts. And if you do work out that math, you see that the admittance seen by those two inverters, well, first of all, it's conjugate of one another because of the symmetry of everything that I've talked about, and is given by a nice simple mathematical expression that depends on the phase shift that you have between those inverter legs, as well as the input-output voltage and some other system parameters. Okay, and you can make this susceptance be exactly zero, so as to get a purely conductive load if you set that phase shift by this particular arc cosine formula, right? And how does this kind of look if you actually plotted this susceptance? You can see it right here, that there are particular values of phase shift where the susceptance goes through zero. Now, of course, that value of phase shift depends on the input and output voltages, assuming everything else is constant, and these are sort of the places that will go to zero. So I can basically put all of this information in a microcontroller and adjust this phase shift by measuring the input and output voltage, or by measuring the input voltage and knowing what output voltage I want to regulate it at. Okay, and then I can essentially get what I want. Okay. Now, another nice thing about this, which is really different from compared to other resonant tanks and other resonant converters, is that the value of the phase shift that I need for different values of input and output voltage is such that as my input voltage increases, the conductance that the inverter see is actually decreasing. Okay? And the power that I'm delivering is V squared, the input voltage squared, times the conductance. So since the conductance is going down as the voltage is going up, I have the possibility of maintaining roughly constant output power, which is really good if I'm going to use burst mode to control the output of the system. Okay, so here is the expression for output power. Okay, and you can see it plotted here against input voltage, and you can see how flat it is relative to if you were just using a series inverter, a series resonant converter, or a parallel resonant converter, or an LLC resonant converter, or any other type of resonant converter, which all it has was a single inverter feeding a resonant tank. You would always have some form like this, where essentially the power would scale with input voltage. You get some V squared times some conductance, which will, yes, depend on the output voltage and some other factors, but it would, you couldn't make it flat without having the second inverter that we added in our system. So that's really the powerful thing that the impedance control network provides with these two inverters feeding it, is essentially a flat output power curve, which means that when I burst it on and off to control output power, I burst from a fairly flat power, so I do not have to over design my system for very high power ratings and then have to burst down from there if the high under a high input voltage condition. Okay. So let's see how this works out. I'm going to apply this first to a particular application. Here what we first consider is basically a solar module which is interfaced to a DC distribution system. The solar panel has an input voltage, has a voltage of 25 to 40 volts. So that's the input voltage spec for this converter. An output voltage that has to be regulated between, or has to sort of, this could be a battery on the output, so the output voltage could be 250 to 400 volts, or 410 volts as is sort of the, or I think it's 260 to 410 is the new emerging DC distribution voltage standard, and roughly 200 watts of output power. So that's the specs for which we build our first prototype. Again, this is sort of the design of it. Again, the way you want to design it is so that it can deliver 200 watts for all of that operating regime. The minimum amount of power is delivered when you have the minimum output voltage. So if you size it for minimum output voltage and you size it so that you have the ability to deliver that power at the extreme input voltages. And ideally what you want to do is design it such that at the minimum input voltage and at the maximum input voltage, because this is sort of the concave shape of this power curve, you deliver the same amount of power. That's sort of the optimal way to utilize this, because then you again have to burst from the least amount of peak power. You can plug in those requirements and you get very nice design formulas that drop out of essentially all of this analytically, and you can figure out the turns ratio that's optimum, and you can figure out the differential impedance that you need to add from here. Of course, the exact values of NLC, for that you also need to figure out or have in your design what value of tank Q you want to use. And I'm not going to discuss that too much, but tank Q plays an important role in the performance of this. If you have a very high tank Q, you'll get nice sinusoidal waveforms, but you'll have more conduction losses. On the other hand, if you have low Q, you can achieve higher efficiency. In fact, we saw that with fairly low Qs, you can get very good performance from this and very high efficiencies. And that's some of what I'll show today. Here's the prototype. This is a 200 watt, 500 kilohertz ICN converter prototype using